Now we will see the ideal solutions and non-ideal solutions. Ideal solution means the solutions which obeys the Raoult's law at all concentrations and temperature is known as the ideal solutions. Non-ideal solution means the solutions which does not obeys the Raoult's law at all concentrations and temperature is known as the non-ideal solutions. So in that first we will see the ideal solution. So in ideal solution, the intermolecular force of attractions between the solute and solvent is similar to solute and solvent to solvent. And one more point is the change in enthalpy of these ideal solutions is the zero, and change in volume of the mixture is also zero. So in ideal solution, observed vapor pressure is equal to calculated vapor pressure from the Raoult's law. Now we will see these points explanation. So in ideal solutions, for example, A to A, this one is the solute, and B to B, this one is the solvent. So between the solute to solute, some attractive forces are present. Between B to B also some attractive forces are present. When we are mixing this solute and solvent, we can get the solution AB. Means in between A to B also some attractive forces are present. Whatever the attractive forces are present between A to B, the same attractive forces are present in A to A and B to B. Such type of the solutions are known as the ideal solutions. And in ideal solutions, change in enthalpy of mixture is equal to zero, means there is no change in enthalpy of solution. And here same, you can take this only. The solute is having some enthalpy, and solvent is also having the some enthalpy. For example, this one is the 10 kilojoules per mole, means the enthalpy of solute is the 10, and the enthalpy of solvent you can take the 15 kilojoules per mole. Now different enthalpies containing solute and solvent, after mixing it can form the AB is the solution. This AB solution is having the 25 kilojoules per mole. Means there is no decrease in the enthalpy of solution, there is no increase in the enthalpy of solution. So that change in enthalpy of mixture is equal to 0, means there is no change. And one more point is change in volume of mixture is also equal to 0. For example, you can take the same solute and solvent. If you mix the 10 ml of solute A and 10 ml of solute B, after mixing these two solute and solvent, we can get the 20 ml of solution. Means is there any increase in the volume of solution? No. Is there any decrease in the volume of solution? No. So that change in volume of this mixture is also equal to 0. Means in change in enthalpy, change in volume of the mixture in ideal solutions is equal to 0. It indicates there is no change in enthalpy and volume. And one more is observed vapor pressure is equal to calculated vapor pressure from the Raoult's law. Now see, this is the solute can exert the some pressure, and the solvent is also can exert the some pressure. And for example, solute A can exert the 1 atmosphere, and solvent B can exert the 10 atmospheric pressure. And here observed pressure is how much? 11 atmospheres. And if you find out the pressures of A and B from the Raoult's law, From the Raoult's law also we can get 11 atmospheric pressure. Means whatever the pressure we observed, that pressure is equal to pressure calculated from the Raoult's law. And one more important point is, in ideal solution, the solute and solvent are having similar mass, similar size, and similar chemical properties. So actually, that point I didn't written here. You can note it. So here, solute and solvent has similar shape and size, and the properties of this solute and solvent is also somewhat similar, not exactly. Okay. And if you observe the examples for this ideal solutions, benzene and toluene, the mixture of benzene and toluene is the example for ideal solution. N-heptane and N-hexane, ethyl chloride and ethyl bromide, carbon tetrachloride, silicon tetrachloride, tertiary butyl chloride, and tertiary butyl bromide. So these are the some examples for the ideal solutions. And next one is the non-ideal solutions. So you actually here I didn't written the properties of the non-ideal solution, because non-ideal solution properties are quite opposite to the ideal solutions. Means based on these points only we can discuss the non-ideal solution. So non-ideal solution means the solutions which does not obey Raoult's law at any concentration and temperature is known as non-ideal solutions. And intermolecular force of attractions between solute and solvent in non-ideal solution is greater than or less than the solute to solute and solvent to solvent. And change in enthalpy of mixture means for non-ideal solutions, non-ideal solutions. So in non-ideal solutions, change in enthalpy of mixture does not equal to zero. It indicates it is make greater than the zero or less than the zero. Change in volume of the mixture is also does not equal to zero. And here observed observed vapor pressure is also not equal to pressure vapor pressure calculated calculated from Raoult's law. Okay, means the properties of the non-ideal solutions are quite opposite. Now already one point we discussed. Here also same, you can take A to A is the solute, and B to B is the solvent. When you can mix these two components, we can get the AB is the solution. So in a AB solution means between the A to B some attractive forces are present. These attractive forces may greater or lesser than A to A or B to B. Such type of the solutions are known as the non-ideal solutions. And change in enthalpy of mixture does not equal to 0, and change in volume is also does not equal to 0. So this is about the non-ideal solutions. And these non-ideal solutions are classified into two types. One is positive deviated non-ideal solutions, negative deviated non-ideal solutions. So at a time we will discuss about the positive and negative deviated non-ideal solutions. So first see the positive deviated non-ideal solutions. In positive deviated non-ideal solution, AB interactions are weaker than A to A and B to B. Means here A to A is the solute and B to B is the solvent. So between the A to A and between B to B, some attractive forces are present, and whenever we are mixing these two components, we can get the AB is the solution. And in this AB solution, the intermolecular force of attractions between A to B is less than A to A or B to B. Means attractive forces between A to B is less than the A to A and B to B. And in a positive deviated solutions, change in volume of the mixture is greater than the zero, means positive sign. And change in a enthalpy of mixture is also greater than the zero, means delta H mixture is the positive, and here also delta V mixture is also positive. How we can say this one? For example, volume you can consider 10 ml of solute is mixing with 10 ml of solvent, then we can get the AB the solution. This AB the solution may have 20.6 ml, means here 0.6 ml of solution is the extra, means change in volume of the mixture is equal to what? Positive, means volume is increases in positive deviated solutions. In the similar way, change in enthalpy of mixture is also positive. Now take again this only, and here same we get the 10 kilojoules per mole energy of solute, and here also 10 kilojoules per mole energy of solvent. After mixing we can get the AB solution, and this AB solution is having the enthalpy is greater than the 20 or less than the 20, obviously greater than the 20. For example, I will take the 20.4 kilojoules per mole. Here also 0.4 kilojoules per mole energy is excess. Okay, next one, vapor pressure of the components A and B is higher than the expected vapor pressure. So here vapor pressure is what? Greater than the A to A and B to B. For example, component A can exert the 1 atmospheric pressure. Component B is also can exert the 1 atmospheric pressure. But the solution AB can exert the more than 1 atmospheric pressure. For example, here you can take the 2 atmospheric pressure, means the pressure exerted by the positive deviated solution is greater than the pressure of the solute and pressure of the solvent. Okay, next one, and one more is this positive deviated solutions is having the minimum boiling point, means here why these are having the minimum boiling point, means we know that A to B attractive forces are less. When attractive forces are less, the strength between A to B is less than A to A and B to B, so that these attractive forces are easily breaks, so that boiling point is less but vapor pressure is more, that you have to remember. So high positive deviated solution having high vapor pressure, and these are having less boiling point. These 2 points are very important. And next one more is this positive deviated non-ideal solutions can shows the minimum boiling point azeotropic mixtures. So about this we'll discuss later. So which type of azeotropic mixtures can show the positive deviation, means minimum boiling point azeotropic mixtures can show the positive deviated non-ideal solutions. And examples for this one is carbon tetrachloride plus benzene. the mixture of carbon tetrachloride and benzene, the mixture of carbon tetrachloride and toluene, the mixture of acetone and carbon disulfide, the mixture of acetone and ethyl alcohol, and ethyl alcohol and water. So these are the some examples for the positive deviated solutions. Okay, so these are the examples. So we can explain this positive deviated solution by taking the example. So you can take the acetone and ethyl alcohol. Ethyl alcohol. Now acetone you can take. Otherwise you can take the ethyl alcohol. So C2H5OH. This is the one ethyl alcohol. And again you can take one more ethyl alcohol. So C2H5OH. And we know that out of this oxygen and hydrogen, oxygen is the more electronegative, so that can possess the partially negative charge, and hydrogen can possess the partially positive. And here also partially negative charge and partially positive charge. Between the partially negative charge of oxygen and partially positive charge of hydrogen, we can get the hydrogen bond. Due to this hydrogen bond between the two ethyl alcohols, we can get the more strength. And if you add the acetone, acetone formula is CH3COCH3. When we are adding this acetone to this pure ethyl alcohol, this acetone will enter between the two ethyl alcohol molecules, and this acetone can break up this hydrogen bond. So when hydrogen bond is break, this ethyl alcohol volume is increases, and this ethyl alcohol volume is also increases. Earlier between these two hydrogen bond is there, so that two ethyl alcohol molecules are somewhat close. Whenever we are adding the acetone, that acetone will enter into the middle, and these two ethyl alcohols will go far. It indicates volume is what happens, increases. That only we discussed here, means change in volume of mixture is the positive because increases. In the similar way this also same, change in enthalpy of mixture also increases. Okay, and we will take the one more examples also. Now you can take the ethyl alcohol and water. Now you can take the water. So this one is the water. Here partially positive and partially negative, sorry, partially negative. Between this we can get the hydrogen bond. So whenever we are adding the ethyl alcohol C2H5OH, this ethyl alcohol can break up this bond. As a result, volume is increases, so change in enthalpy is also increases, and vapor pressure is also increases. So earlier hydrogen bond is there, so that this what two water molecules can exert the lower vapor pressure. So after breaking of this hydrogen bond, these two liquid molecules can exert the more vapor pressure, but boiling point is what, boiling point is less. Okay, this is about the positive deviated non-ideal solutions. Now we will see the negative deviated non-ideal solutions. So before that we will see the graph. Now see here, vapor pressure and mole fraction. This one is the solution, this one the solvent, and this one is the solute. And here this is the origin line is the ideal solutions. So for the ideal solution, vapor pressure is equal to the pressure calculated from the Raoult's law. But in case of positive deviated solution, vapor pressure is greater than the ideal solutions. So that this dotted curve we have to represent above this origin line. And even now you can take the solvent. The vapor pressure of the pure solvent in an ideal solution, this is the origin line. For positive deviated solutions, we have to draw the line above this. Okay, and for the solute also, above this origin line we have to draw. And this is the ideal, sorry, this is the positive deviated non-ideal solutions. And next one is the negative deviated non-ideal solutions are there. So AB interactions are stronger than A to A and B to B, and here we will discuss. See, so as usual A to A and B to B is there. This is the solute and this one is the solvent. So when we are mixing these two, we can get the AB is the solution. And in this AB solution, intermolecular intermolecular attractions attractions are greater than A to A and B to B. So here intermolecular attractions are more in AB solution than the A to A and B to B. Such type of the non-ideal solutions are negative deviated non-ideal solutions. And here change in a volume of the mixture is negative, means less than the 0. Change in enthalpy of mixture is also negative, means it is also less than the 0. For example, here you can take a 10 ml 10 ml of solute is mixing with a 10 ml of solvent, then we can get the 20 or less than the 20 or greater than the 20, we can get a 19.9 ml, means 0.1 ml of solution is less. So that change in volume of the mixture is negative. And even you can take the enthalpy also. Here you can take the 100 kilojoules per mole, and here also 100 kilojoules per mole. For ideal solution we can get the 200. For positive deviation we can get the more than the 200. For negative deviated we can get less than the 200. For example, we can take the 190 kilojoules per mole. Okay, and one more is here A to B attractive forces are greater, so that strength is more. If strength is more, to break up this bond it requires more energy, so that A to B can exert the less vapor pressure. And to break this bond it requires more energy, so that these are having a more boiling point, means positive deviated non-ideal solutions exert the more vapor pressure, they have the less boiling point. But negative deviated one is having a less vapor pressure and more boiling point. So that point only we discussed here. So at AB interactions are stronger than A to A and B to B. Change in volume of mixture is the less than the 0, and that is change in enthalpy of volume mixture is equal to negative. And here change in a, sorry, here enthalpy you can take, change in enthalpy of mixture is also negative. And one more is vapor pressure. You already we discussed the vapor pressure of the component A and B is less than the expected one. And maximum boiling point azeotropic mixture shows this deviation. So here in a positive minimum boiling point azeotropic mixture, negative deviation maximum boiling point azeotropic mixture shows this deviation. And some examples for the negative deviated solutions is chloroform and acetone, chloroform and benzene, chloroform and diethyl ether, nitric acid and water, potassium nitrate and water, phenol and aniline. And this also we can discuss by taking one example. For example, you can take the chloroform and acetone. Okay, chloroform, CH Cl3. This is the solute, and acetone CH3 CO CH3. This one is the solvent. Now, by mixing these two components, we can get the solution. So here carbon, hydrogen, chlorine, chlorine, and then chlorine, and here oxygen, double bond C, CH3, and then here also CH3. So here in a pure chloroform, there is no bond with a solvent molecule. Now, whenever we are mixing these two components, we are getting the solution. In this solution, between the partially positive charge of hydrogen and partially negative charge of hydrogen, we can get the hydrogen bond. This you have to remember. So, which bond is formed between the acetone and chloroform? Hydrogen bond. So whenever the hydrogen bond is formed, all these chloroform molecules and acetone molecules will come closer, then volume is what happens? Decreases. That is the negative. Change in enthalpy of mixture also decreases. That is also negative. So due to the formation of this hydrogen bond, this solution can exert the less vapor pressure, and already we discussed that this one can shows more boiling point because due to the formation of this hydrogen bond. So not only this one, even you can take a phenol and aniline. So this one is the phenol. Now you can take the aniline, NH2. Now this hydrogen has the partially positive charge. On the nitrogen atom, one lone pair of electrons are present. Means that this one can possess the negative charge. So a hydrogen bond formed between the positive charge of hydrogen of phenol and a lone pair of electrons of the nitrogen in aniline can form hydrogen bond. So here between the positive charge of hydrogen of phenol and lone pairs containing nitrogen of aniline, between that two hydrogen bond is formed. So that these two are also examples for the negative deviated solutions. Now we will see that graphical representation. Now here you can take the vapor pressure. Now here you can take the mole fraction. Now this aligns ideal solution, and this is the solvent, and this one is the solute. Now this negative deviated non-ideal solutions are having a more volume or less volume than the ideal solutions? Less. So that dotted lines curve we have to represent downside, and vapor pressure of the pure solvent is less than the ideal one. So that these dotted lines are also downside, and here also downside we have to represent. Now you observe these two. In positive deviated non-ideal solutions, the dotted curves are above the origin lines. For this above, and for this also above. For this also, this is the above. And negative deviated non-ideal solutions, the curves should be downside. Okay, so this is about the ideal, non-ideal, positive deviated, and negative deviated ideal solutions. And the next one is the azeotropic mixtures. Okay, this is the very important. Azeotropic mixture means the mixture of two or more components which like pure chemical compounds boils and distills at the same temperature without change in composition throughout the mixture is known as the azeotropic mixture. And for example, A, B is the one solution, C and D is the one solution. These two solutions can boil at a same temperature. Means solution AB can boil 100 Celsius, and solution CD also can boil at 100 solutions. While boiling, there is no chemical change in the solution AB and the solution CD. Such type of the solutions are known as the azeotropic solutions. Okay, is definition is very important for 1 mark. So mixtures of two or more components which like pure chemical compounds, and that two chemical compounds will boils and distills at the same temperature. At that temperature there is no change in the composition of the mixture. Such type of the mixtures are known as the azeotropic mixture. So these azeotropic mixtures are two types are there: azeotropes with a minimum boiling point and azeotropes with a maximum boiling point. So already in a positive and negative deviated solutions we discussed. Here see, minimum boiling point azeotropic mixture shows this deviation means positive deviation. Now here see, minimum boiling azeotropic with a minimum boiling point, which type of solutions? Positive deviated. Deviated solution shows this mixture, and this positive deviated solutions are having less vapor pressure or more vapor pressure. This one can shows the more vapor pressure, and boiling point is less. Now azeotrope with a maximum boiling point. So which type of deviated solutions? Negative deviated solutions shows this one, and these are having a more boiling point and less vapor pressure. And very important point is azeotropic mixtures does not separated by the fractional distillation. So this point is very important. Azeotropic mixtures does not separated by fractional distillation, because these azeotropic mixtures can boil and distills at a same temperature without change in chemical composition.